Hello everyone. Today we are going to learn about the periodic table. So what is the periodic table? We are going to learn about various topics about what is the periodic table and other things also. What is the periodic table and other things as well. So let's start. Okay. So first of all, let's say the names of elements from 1 to 20. Number 1 is helium, hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So these are the first 20 elements that everyone needs to know. It's much better if you learn it till 30, but even if you learn it till 20, it's fine. So now let's learn about modern periodic table. So I'm going to represent modern periodic table by MPT. So we are going to write what were some major points. It was developed by Moseley. So who is Moseley? Moseley is a scientist which discovered this. So what this states, this is based on atomic number. So what does this mean? It's that it states that all the physical and chemical properties of elements are periodic function of the atomic number. So when we arranged hydrogen, helium, like we did this was done on the basis of atomic number. Here, hydrogen has the atomic number of 1, helium has the atomic number of 2, continuing to 20, and there are more than that. So now we are going to talk about periodicity that is caused due to modern periodic table. It means that repetition of elements with similar properties after regular interval of time. This happens because repetition of similar valence cell electronic configuration. So we know that like a modern periodic table looks like this, not exactly, but like this. And we have groups over here, which I'm going to talk about later. And here, let's suppose alkali metals or 1A or first group, they have similar properties due to periodicity. And this is because of the way that we have arranged in modern periodic table. So we are going to talk about some magic numbers. So what are magic numbers? They are basically numbers that are found, or like the number of rows and groups, not the number of elements in a row. It goes like 2, 8, 8, 18, 18, and 32. These are the magic numbers. You don't need to know the meaning. I'm just telling you. So now let's learn about the father of periodic table. Father of periodic table. So who might be the father of periodic table? Make your guess. If you said Moseley, you are wrong. But Moseley is not the father of periodic table. The father of periodic table is Mendeleev. Why? Because he created the first successful periodic table. Now let's continue to learn about main features of modern periodic table. The main features are number 1, group, and number 2, periods. So what are groups? Groups are vertical columns, and there are 18 of them, whereas there are only 7 paired and they go horizontally. Here, groups is due to from the IUPAC system, they are numbered from 1 to 18. But in the old system, it was done from 1A to VIIA, 1B to VIIB, VII, and group 0. So now we are going to learn on the basis of 1A because it is much easier for beginners. So now let's talk about some groups and their names. So the first group also known as alkali metal. They are located in 1A, and their general formula is NS1, and they have one valence electron. Because here is 1, there is one valence electron. So now let's talk about the second one. The second one is alkaline earth metals. Alkaline earth metals. So they lie in 2A, NS2 general form, and 2 valence electron, because here is 2. Now let's learn about the 13th. This is 3A, but it is 13th in the group, because in the periodic table, here and here are the first and second, but after that it goes over here, because over here this is the part of B. So now we go to the 13th, which is boron family. So boron family is 3A. General form is NS2 and NP1. Here 2, 1 means it has 3 valence electron. Now let's learn about 14th group, which is carbon family. So carbon family, which is 4th A, has the general form of NS2, NP2, and I want you to tell me the valence electrons of this. Yes, it is 4, because 2, 2, 4 valence electron. Now let's talk about the 15th. 15th is nitrogen family. They are also known as nicogens, which means urea forming, because nitrogen forms urea, and nitrogen is a part of this group. They are represented by Va or 5A, and their general form is NS2, NP3, and their valence electron is 5. And the 16th group is oxygen family. Oxygen family is also known as chalcogen, which means ore forming, because they form ore. They aren't ore, like oxygen is not an ore, but they form ore. And they are represented by 6A, general form NS2, NP4, valence electron 6. Now let's go to the 17th. 17th is fluorine family. And fluorine family is also known as halogen. Halogens means salt forming, salt. General form is NS2, NP5, which means they have 7 valence electron. This means the max amount of valence electron is 8. So if it has 7, it means it is very reactive. Now let's go to 18th, zero group. It is also known as zero group inert gases, inert gas or noble gas. They are known these because they do not react. Why? Because their general form is NS2, NP6, except for helium, because helium is 1s2, and they have 8 valence electron, except for helium again, because helium has only 2. So why they are neutral? Because it has 8 electrons. So let's suppose a electron, some of the element, and if there are 8, let me change the color to make it easier. 1, 2, 3, 4, 5, 6, 7, 8. If there are 8, if another electron tries to get in, or another element tries to take an electron, they don't react. they don't like to give up their electron or take electron because they are already satisfied and they want to save their energy. But this is a general case. Sometimes electrons are taken and given as well. Now let's talk about periods. There are the 7 rows are called periods. They are indicated by 1, 2, 3, 4, 5, 6, 7. And number of period is equal to the number of cell, outermost cell. So let's suppose helium. Helium is defined by 1s2. Here, 1 signifies it has only one cell. So if you look at helium, it only has one cell with 2 electrons. Similarly, for other elements, it will have 2 if it has 2 something, 1 if it has, and similarly it goes on. Now, the number of elements in each period is equal to the number of electrons required to fill the various orbitals present in that outermost cell. So basically, here, now let's look at this. In the first period, 2 elements can be stored. 2 elements is stored, not can be, but it's made by humans, so it's made for easy to learn, to make it easy to learn. 2 elements, so this is known as very short period. The second one has 8 elements and is known as short period. Similarly, the third also has 8 elements, so it is known as short period. The fourth, fifth have 18 elements, so they are called long period. And sixth has 32 elements and is called very long period. 7 is still incomplete because there are still position left, but it is still called very long period. Now let's talk about the advantage of periodic table. The first advantage is it removes most of the defects of Mendeleev's periodic table. The places of isotopes have also been justified because isotopes have same atomic number. So in modern periodic table, which is based on atomic number, it works. But in Mendeleev's periodic table, it is based on atomic weight. So since atomic weight of isotopes is not the same of the element, this does not work, and hence this is a much better system. Now let's talk about the second. It explains periodicity. We already talked about periodicity, which means the repetition of similar characteristic elements after similar time. And another is, since atomic number is a more fundamental property. So think about it. Atomic number is the number of protons or electrons. But atomic weight is the sum of protons and electrons, the average sum. So this is not such fundamental as this, where it only takes one value, here it takes more values. So atomic number is more fundamental property of an element, so it is much better. Another one is the places have been specified. So in the periodic table, we can know this part are metal, this part are non-metal, and these are metalloids. Basically, the periodic table is treated like this, where metallic character decreases going here. And lanthanides and actinides. So when I was drawing periodic table, I was only making this, but there is also a bottom layer over here, 2 layers. So 1, 2, 3, 4 like this. So these are lanthanide actinides are kept below the periodic table with reason. The reason is that keeping it over here will make the periodic table longer, and which is not like that good. So because it will take more space, this is much more space efficient and easier to learn. Now, the elements have been divided into 4 distinct blocks. The blocks are S block, P block, B block, and F block. We'll learn about this because this is also very important. So now let's learn about SPDF. So this can be learned under the topic classification of elements in the modern periodic table on the basis of differentiating electron. The last electron is called differentiating electron. For example, in 1s2, 1s1 and 1s2 are its components. If we think about it, where these two represents two electrons, but in this case we are representing is this is the second electron. The second electron comes after the first electron. So here, this electron, where this goes, it determines. So let's take another example. 1s2, 2p1. Here, the last electron is on the p cell, so it is p subcell. Similarly, any number of electrons are arranged in SPDF. Not in this, but if it goes on S block, S, it will be S block, P, P block, and similarly, and so on. On the basis of orbital in which differentiating electron enters, there are 4 blocks. Now let's talk about S block elements. So what are S block elements? It is the elements which last electron or differentiating electron enters in S orbital. Orbital. Remember this word. This is important. Orbital. Now, it includes 1A and 2A, which we learned. 1A is alkali metals, 2A is alkaline earth metals. Now, let's talk about the general characteristics. The general characteristic is their general configuration is 1 or 2. Here, it can be NS1 or NS2. You can add any number over here, like 1S1, 1S2. These are all part of S block. Oh, sorry. This is not part of S block. Now, I'm quite not sure about like this 1s1 and 1s2. So I don't know about this, okay? So let's not check it. I'm just saying that the general case is 1 NS1 or 2. Now, they are highly reactive soft metal. Why they are highly reactive? Because let's say something is like this. It will want to take electrons. So let's take an example. Suppose this means that here it only has 1 electron in the outer cell. How many cells? It has 1 or 2 outer cell. So it will like to give electron. So it is highly reactive because if it gives 1 electron or 2 electron, it will be stable and thus it wants to lose the electron. And they have low melting point and boiling point, good conductor of heat and electricity because they are metals. And metals, as we know, are good conductor of electricity and heat. They form ionic compounds, and so +1 and +2 oxidation state. So what are oxidation state? We'll also learn that in a later video. So what is ionic compound? Ionic compound is, let's say, Na plus Cl, NaCl. This is an ionic compound. Why? Because Na is a metal, and metal with non-metal gives ionic compound. Now let's talk about they are strong reducing agents. So what are reducing agents? They are the agents that oxidize another element and get reduced themselves. Now they impact on the color of flames. For example, if we take a flame, I think red color would suit this much better. If we take a flame, let's suppose we add Na, which is sodium, which is a metal. It will turn its color to gold and yellow color. So instead of red or orange like this, it will turn like this. It will change color because we added Na. Now let's learn about P block element. They include 3A, 4A, 5A, 6A, 7A, and 0 group. Their general configuration is NS1, NP1 to 6. So these are the factors that depends or change. Sorry, this is 2A, 2, not 1, 2. So we have to look over here. Now, they includes metals, non-metals, and metalloids. In the periodic table, they lie over here. The ionization energy are higher than those of S block. Ionization energy, short for IE, we will also learn about this later on, is also higher than S block elements. They mostly form covalent compounds among themselves and ionic compounds with metals. Let's say Na plus Cl. We take the last example, NaCl. They'd like to form covalent bonds with themselves and ionic bonds with metals. Now they are mostly electronegative in nature and show variable oxidation states. That means in S block it only stored one plus or 2 plus. Here it can be variable. It can be +1, +2, +3, -1, -2, -3, so on. The oxides are generally acidic in nature. So, for example, P2O5 is acidic, SO2 is acidic, CO2 are acidic. So, I will show you an example. C plus O2, CO2. These both are P block element, so they form a covalent bond. But if we combine a P block element with the S block element or metals, they form ionic compounds. Now let's talk about D block elements. The elements whose last electron falls in d orbital. D orbital of n-1 cell. Up till this point, we have looked at only the last cell, but now we are looking at the penultimate cell. This is known as penultimate set, n-1. So now they are also called transitional elements because they lie between S block and P block. So in a periodic table, they lie over here. Here is S block, here is P block, and here lies D block. So it's a transition. Metals, non-metals, generally non-metals, and metalloids. They include 2B, 4B, 5B, 6B, 7B, 8, 1B, and 2B. So let's say what is volatile metal, because this is like a nice note to remember. Volatile metal means group 2B, such as mercury, cadmium, indium. So why these are volatile metal? Because they are dangerous for human to touch. So we should not touch them. Now let's talk about the general characteristics of D block element. They are basically so we talked about penultimate cell. This is why, because we have to look over here. Even though there is n over here, we have to look at n-1. So even when searching for D block element, you don't want to consider this as, if you see this, don't be like S block. You have to notice this as well. They are hard metals having high melting point and boiling point. This is just know this. Metals, non-metals, metalloids. So Up to this part, you can write good conductor of heat and electricity. Hard metals, high melting point and boiling point. Good conductor of heat and electricity. Now, let's talk about other characteristics. They show variable oxidation states. Let's, for example, Fe. Fe shows +2, +3, and even +1 in some cases. So they show variable valency. And they form color compounds. For example, let's take SuSO4 5H2O. This is a compound formed by D block elements, which is known as blue vitriol. And from the name, I think you can guess the color. It's blue. And similarly, FeSO4.7H2O is known as green vitriol. And from the name, I think you know, it's green in color. And they form complex compounds. For example, we look at NaCl, CO2. These are simple compounds because they don't have many elements and are formed simply. But over here, you can form crazy compounds, like very complex, like K4, Fe, CN6, bracket close. Look at this. This is such a complex compound. There are two brackets over here. So they can form complex compound. And most of them have catalyst properties. What are catalysts? They increase the rate of reaction. The most common catalysts are iron, nickel, platinum, etc. They are less electropositive than S block, but more electropositive than P block. So just know this. Electronegative, kinda in the middle, and electropositive. Okay? Oh, sorry, I meant to say positive, negative over here. So now let's learn about F block, which is the final block. Here we look at the anti-penultimate cell, which means third last. And its spelling is ANTPEN ultimate. So you could remember this by remembering ANTE, pen, and ultimate, which means N-2, because this is third. First cell, N-1 second. So this is first, penultimate, then anti-penultimate. So their general configuration is N-2, F1 to 14, N-1, D0 or 1, and NS2. Now, they are heavy metals with high melting point and boiling point. They form color compounds. They show variable oxidation state. And all actinides are radioactive in nature. We talked about actinides and lanthanides at the bottom guys. And here, these are the F blocks. But since these are just a part of the periodic table, but are removed because to make the periodic table shorter, they have similar properties to D block elements. Now let's talk about some disadvantages of modern periodic table. The position of hydrogen is not defined. So we know hydrogen is 1s1. But its position is is defined. They have given a reason, but it's not sufficient. Now, and the outer electronic configuration of helium. Helium is 1s2. Is similar to group 2 elements, but is placed on group 18. So if you look at the periodic table like this, hydrogen is here, helium is over here. So helium is 1s2. It is similar to group 2 elements, but is placed over here. So this is also properly not defined. The drawing is not for scale because this is way too big. So this is valence cell N. This is penultimate cell N minus 1. This is anti-penultimate cell N minus 2. So atomic radii. Now let's talk about nuclear charge. So first of all, let's talk about shielding effect. In a multi-electron atom, which means it has multiple electrons, the electron present between nucleus and valence shell are called intervening electrons. So there are electrons over here and electrons over here. So this is intervening electron of this. Now they cause a force which reduces the nuclear attraction on the valence shell, which means this cell. So this is called screening effect or shielding effect. So basically, I will again describe this because I kind of stuttered. We have 2 electrons over here and some electrons over here. The nuclear force tries to push them inside, but these intervening electrons block them and reduce the force acting on them. So this is called shielding effect. The greater the number of electrons, the greater the shielding effect. So here 2, 2. So the shielding effect will be less. But if there here is more, and also there is another layer, this will have more shielding effect here. Now let's talk about effective nuclear charge. Effective nuclear charge is also known as ZEF, where this EF means effective, Z means nuclear charge. It is equals to nuclear charge, which is denoted by Z, minus shielding constant, which is denoted by. Now, the actual charge experienced by the valence electron as a result of shielding effect is called effective nuclear charge, this. Now, let's show the periodic variation of shielding effect and ZEF. I'll create a small diagram. This is group as we go down. This is period as we go sideways. Shielding effect, ZEF. So now we will talk about what happens. The shielding effect as we go down a group increases. The shielding effect as we go left or right to a period stays constant, because 2 electrons, 1 electron, 2 electron, how many electrons we have, the shielding effect is constant because there is only 2 electrons. The number of here does not change. And ZEFF increases when we go here and decreases when you go down, because as we go down, the cells, there are more cells, they get bigger, so the force acting on him is less. But if we go closer to here, then since there are more electrons, the nuclear power will increase, due to which, and since the shielding effect is constant, the effective nuclear charge will be more. Now let's talk about periodic properties, atomic properties. The various properties of an element like atomic size, ionic energy, electron affinity are directly related to the electronic configuration of atomic structure of an element, which is known as atomic properties. The properties of atom is atomic property. Now let's talk about atomic radius or atomic size. Atomic radius is the distance from the center of the nucleus to the outermost cell containing the electron. So let's take electron, atom, I mean. This distance, which we can call r, is known as atomic radius. Atomic radius cannot be determined precisely because we just can't take like a single element and just count the pixels. Since an element is not as simple as this, it is much more complex, which we will learn in a future video. So it is very difficult to isolate a element or atom, not an element, atom. So atomic radius is measured indirectly in the bonding condition and generally expressed as follows. There are several methods. Let's talk about some, which is covalent, covalent radius, van der Waals radius, and ionic radius. Covalent radius is the half distance between nuclei of atoms bonded by single covalent bond. So a covalent bond looks like this. So this will be some distance. If we divide it by half, it will be r. Since you can see it is a little bit farther, and since so it is not accurate, but it's the best we can do. And van der Waals is, it's not touching and it's half distance, so it's a little bit more. And van der Waal is a force, it's not a bonding, so no bonding is occurring here since there is a gap. This is a force. So it is the half distance between two non-bonded nuclei of atoms held by van der Waals force of attraction. And ionic radius is this, r. A distance between the center of the nucleus and a point up to which the nucleus has its influence on its electron in an ion. So what I meant to say is, let's first of all draw this. So this is plus charge, this is plus charge, this is negative. Distance between two nuclei is this. This is ionic radius of cation, and this is ionic radius of anion, which we will learn what is cation anion. We will also learn that. A conclusion obtained by the study of ionic radius. A cation is smaller than its parent atom. Now we will learn about cation, and the size of cation is smaller than the size of atom because of the following reason. Number one, increase in GeF, which is effective nuclear charge. A cation contains less number of electrons than its parent atom because the nuclear charge remains same. Therefore, effective nuclear charge in cation and electrons are more strongly attracted to the nuclei, resulting in decrease in size. Number two, removal of valence shell. So this I will show you an example. Let's take an electron. So normally it will have, let's say, suppose one electron. So when it is a cation, it will have a plus charge because it lost an electron, and due to which it will lose this cell. Since it will lose this cell, the shielding effect is reduced, so the force acting on it will increase. Let's suppose here Fe plus 2 plus, and Fe plus 3 plus here. The atomic number of them are, this is atomic number and this is number of electrons. Here 26, 24, 26, 23. You can see how, because here is plus 2, which means number of electron is less. So it drops now. Here, nuclear charge is constant because atomic number has not changed. Which means that number of proton and neutron has not changed. So the nuclear attraction is same. The number of electron decreases as we go from here to here. Shielding effect decreases because the number of electrons have decreased. Effective nuclear charge increases because shielding effect decreases. Nuclear attraction on valence shell increases because either we have lost a cell or we have decreased the number of electrons, and radius decreases. Now let's talk about size of cation decreases with increase in positive charge on cation, because on increasing positive charge on cation, effective nuclear charge increases. So we are basically talking about what we talked about. The size. So let's say, let's take 2. If we have an extra electron over here and if we only don't have the extra electron, the size of this will be bigger because it has one more cell, plus it is suffering less force, so it will be bigger. Here it will be suffering more force, so it will be smaller. Now let's talk about anion is bigger than its parent atom. It is similar as for cation, but exactly opposite. So let's take this. Anion contains more electrons than its parent atom, but nuclear charge remains constant. Hence, effective nuclear charge decreases in an anion, and electrons are less strongly attracted by nucleus than its parent atom, resulting in, so let's take chlorine. Chlorine has 7. So this is basically chlorine. And if we add another one, we will have 8. So here, when we add on this new electron, what this does is increases the shielding effect. So the force acting on it will be less. So I will quickly describe what are what. So let's take an atom. If it is a cation and anion, if it's a cation, it will have plus charge and will lose electron. It becomes anion, it will be minus charge and it will gain electron. Lose electron, gain electron. Now, let's take a few example questions. Why is size of Cl minus ion larger than size of Cl? And whereas size of K plus ion is smaller than Ki. So this can be described because this is an anion, because it gained electron. So the effective nuclear charge decreased. So it got bigger. Here, exactly opposite. Effective nuclear charge decreased. So that is the reason. So now let's talk about in isoelectronic ions. Ions having same number of electrons but different nuclear charge are called isoelectric ions. I'm going to tell this again. Ions having same number of electrons but different nuclear charge are called isoelectric ions. So let's take example. N minus 3, O minus 2, F minus Na plus 1, Mg plus 2. Here will be atomic number and here will be number of electrons. 7, 8, 9, 11, 12. This is the atomic number, but the number of electrons is same. So now we will take the basic logic techniques to find out. Here, nuclear charge increases because the atomic number, greater the atomic number, greater the nuclear charge. Number of electrons remains constant as we go from here to here. Effective nuclear charge increases. Why? Because the nuclear charge is more. Nuclear charge on valence electron increases. Why? Because effective nuclear charge is more. And radius decreases because more nuclear charge means that radius will decrease. Now, let's talk about the variation of atomic radius in periodic table. In a group, as we go down, number of cell increase and size of atom also increase. So let's take some example. Lithium and Na. Lithium has 2 cells, so it will not be as big as Na, which has 3 cells. I think you can get my point. It only has 2 cells, it has 3 cells. So the force acting on this will be greater, the effective force, than this. So due to this more sealing effect, which we can see because of since there is more sealing effect, this will be larger. So as we go down, size increases and number of cell increases. Now let's talk about in a period. Period means going like this. Effective nuclear charge increases, so size decreases. So you might be, what? Huh? So I will tell you what. So let's take lithium and beryllium. So we know lithium has 1 on the outer, but beryllium has 2. Its atomic number is 3 and it's 4. So we know that this beryllium will have more nuclear attraction than lithium. But here we don't see much difference in sealing effect because there is like no other cell. It's only 2 cells on both of the conditions. So the sealing effect that is caused on this because of an extra electron is very less compared to the increase in nuclear attraction. So effective nuclear attraction also increases. Hence, the size decreases. So I will show you another diagram which will make it pretty clear. Group, radius, period. Going down increases, going this way decreases. Because here, new cell is added and here, nuclear power is increased more than nuclear cell. So now, let's talk about ionization energy or ionization potential, which is represented by IE or IB. It is the amount of energy required to remove the most loosely bounded electron from an isolated gaseous atom in its ground state to produce cation. Remember this, isolated gaseous atom in its ground state. So let's take an atom. So this can be regarded as the most loosely bounded electron. So to remove this, how much amount of energy is required when it is isolated gaseous atom in ground state to produce cation is known as ionization energy. Now let's talk about second ionization energy. It is the amount of energy required to remove the second electron from a monovalent cation to atoms to form divalent cation. Divalent cation means +2. Monovalent means +1. Mono means 1, di means 2. Now let's talk about successive ionization energy. Here, the first ionization energy is less than second ionization energy, which is less than third, and so on. Why? Because take an atom. Let's suppose it has 3. Here, since there are 3, the effective nuclear charge is very low. So the first electron comes out pretty easily. But if we only have 2, the effective nuclear charge increases because the electron number is less. So the second will require more. Similarly, the same will occur for the third because it will have the most among them 3. So as we remove more and more electrons, the ionization energy also increases, not decreases, increases. Because ionization energy is the amount of energy required to remove the most loosely bounded element from an isolated gaseous atom in its ground state to produce cation. So if there is more more nuclear charge or effective nuclear charge, it will require more ionization energy. Now let's talk about factors affecting ionizing energy. Atomic size. So when going here, which means period, atomic size decreases and IE increases. Why? Because since atomic size decreases, it requires more energy to remove an electron. Because the size decreases, so it will require more energy. But in group, as we go down, atomic size increases, so IE decreases. So what this means is atomic size is inversely proportional to IE. So you can remember this way so that you can know. If atomic size increases, IE decreases. So they are opposite. Nuclear charge. So let's take over here, period again. If nuclear charge increases, then IE also increases. Why? Because we already talked about it. If nuclear charge increase, IE increase. It is a basic concept because if it attracts more tightly or more with more force, then to remove an electron, it will require more energy. Now let's go over shielding effect or screening effect. Therefore, IE or ionization energy decreases with increasing screening effect because if you have two electrons, the force will be more if we had another set of cell or which increase the screening effect. So if it is more tighter, then it will require more energy. And electronic configuration. Half-filled and completely filled orbitals are stable than other configuration. More energy is required to remove electrons from stable orbitals. Thus, more stable electronic configuration, greater the will be IE. So what this means is, let's take helium, which has 2 electrons. This will require more energy. Why? Because it is stable. And why it is stable? Because it is two electrons. If an electron doesn't like to take electron or give electron, it is in stable condition. Helium is in stable condition. That's why you have never seen a compound when helium combines. It is always He for He. You have never seen He2 because it doesn't combine with itself, or HES or any other combination because they don't combine. And the nature of orbitals. So when looking at the periodic table, we see this pattern. Here, distance from nucleus increases. Why? Because whenever creating cells, the S comes at first, P, D, and F. So the closer, the more powerful. Penetration power of orbital decreases going here because this is much farther than this. Nuclear attraction decreases, so IP also decreases. Now let's talk about in successive ionization energy. Cr, Cr plus, Cr plus plus, Cr plus 3. Atomic number of electrons. 24, 24, 24. Because the atomic number doesn't change even if we lose or gain electron. 24, 23, 22, 21. So going from here to here, the number of nuclear charge remains constant. Electron decreases. You can clearly see. Nuclear attraction on valence shell increases. Why? Because number of electrons have decreased, which means shielding effect also has decreased since number of electrons have decreased. This means effective nuclear charge has also increased, which means radius has decreased, so IE has increased. If radius is smaller, IE increases. So when effective nuclear charge increases, IE increases. When radius decreases, IE increases. Now, let's talk about variation of ionization energy in periodic table. In period, on moving left to right, which means like this, here to here, nuclear charge increases and the size of atom decreases, due to which electrons are more strongly attracted by the nucleus and more energy is required to remove electron. Some elements show irregularities in general trend. This is due to the extra stability of half-filled and completely filled orbitals. So, if we go and write over here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Here, these two don't like make sense because they are half-filled. Specifically, here, Be is 1s2, 2s2, and N is 1s2, 2s2, 2p3. Here it is full-filled and this is half-filled. So this result, this unexpected result can be found. It is not unexpected, but like in general, people do not expect this to happen. So we know that the ionization energy of this is greater than this. Now in group, on moving from top to bottom in a group, the nuclear charge increases. However, its effect is negligible when compared to the effect of increased screening effect and the size of atom. Hence, electron experiences less attraction force and consequently IE decreases. So, when going down, nuclear charge increases. Going down, screening effect also increases. When going down, atomic size increases. Why? Because the screening effect is much greater than attraction and IE decreases. Here, it is a conflicting result because we mostly know that Z is directly proportional to IE. What I haven't told you is the more accurate version is ZFF is effective nuclear charge is directly proportional to IE. If screening effect is more than increase in nuclear charge, then the effective nuclear charge is less. Now let's talk about electron affinity. So what is electron affinity, which is also can be written as EA? The amount of energy released when an electron is added to an isolated gaseous atom in its ground state to produce anion is called EA. It can be expressed in the process. Let's take A, X, isolated gas, so it will be represented by G plus E minus X minus G plus energy. So the greater amount of energy released, higher will be the EA, which means if greater energy is released, the EA will also be greater. In addition to first EA, second and third EA are known. However, the addition of second electron to the negatively charged ion is opposed by interelectronic repulsion, and hence energy has to be supplied for the addition of second electron, which means due to the repulsion between the electrons, it requires more energy. Now let's talk about factors affecting electron affinity. Atomic size. As atomic size decreases, distance between nucleus and incoming electron decreases. As a result, force of attraction between nucleus and incoming electron increases. Hence, EA will increase. So what this means is, let's take a atom. If its atomic size decrease, it's smaller than this, let's suppose. When it decreases, the distance between nucleus and and force nucleus and the valence shell decreases, which means the force attracting is more. So if we add an electron, it will quickly go there. So as atomic size decreases, EA increases. Now effective nuclear charge. As effective nuclear charge increases, the force of attraction between nucleus and incoming electron increases. Hence EA increases. Like in the last case, because force has increased, the electron could quickly get in. So ZEFF is directly proportional to EA. I think you have not gotten the concept of EA because I didn't describe it pretty well. So what it means is, let's suppose the electron, how much energy is released when it has taken this electron. That's the electron affinity. Electronic configuration. Elements having stable electronic configuration like half-filled and completely filled electrons have EA either very low or almost zero, as they do not accept additional electron easily. This can be explained as, or let's take at 2A, which contains beryllium, Mg, Ca, etc. Their last is generally NS2, which is fulfilled. So their EA will be zero, because like when they're fulfilled, they don't like to take more. So if they are fulfilled, they don't like to take electron because they don't want to mess up their stable state. So their electron affinity is almost zero. In noble gases, it has NS2, NP6, which is also stable. So they also have EA of almost zero. In group 5A, which contains elements like nitrogen, phosphorus, they are half-filled. So half-filled, so their general configuration is this. So they have very low tendency of gaining electron and has EA value very low. Electron affinity of halogens, or this. Here, NS2, NP5. In here, we see it is not even half-filled and it is not fulfilled, but it requires one electron to be stable. So it has high EA, extremely high, like crazy levels of high, because if it takes one electron, it will be stable. And that's the goal of all the electrons. The variation of electron, now let's talk about the variation of electron affinity in periodic table. In period, on moving left to right in a period, nuclear charge increases and the size of atom decreases, due to which tendency of atom to attract incoming electron increases, hence EA increases. However, some elements show irregularities in this general trend due to the stability of their electronic configuration. So going here, generally EA increases, but sometimes for some cases they don't. For like BE, it's almost zero, NE is almost zero, and NE is almost zero when going from here to here. Now let's talk about in group. On moving from top to bottom in a group, atomic size increases, due to which tendency of atom to attract incoming electron decreases, hence EA decreases, which means atomic size increases, so EA decreases. This is why, because when atomic size increases, it implies that the nuclear force is less, due to which EA decreases. In case of halogens, when we suppose that F, it should be in the form of this, but no, it's not in the form of this. It's actually in the form of ClFBrI. You might think why? Because electron density of fluorine is high due to its very small size, and added electron experiences high inter-electronic repulsions. Hence, added electron experiences less nuclear attraction than fluorine than in Cl atom. Consequently, EA in F is lower than in chlorine. So let's show with a small diagram. In F, it's like this. So it's very packed. They are already packed. So when taking a new electron, they will hesitate because they are already so packed, and taking another electron will make it more packed up. But in here, there is space. So when taking electron, they will gladly take electron. So now let's talk about electron negativity. So what is electron negativity? Electron negativity of an element is the tendency or ability of an atom in a molecule to attract the shared pair of electrons towards itself. So let's take in HCl molecule. Here, the shared pair of electrons lie towards Cl mode. Yeah, like this. Why? Because Cl is more electronegative than hydrogen. Electronegative is generally measured in Pauling scale, spelling P-U-P-A-U-L-I-N-G, Pauling scale or Mulliken scale. These are not the same scale, these are like different scales, but Pauling scales is most used. So this is like the golden boy, Pauling scales. Now let's talk about factors affecting electronegative. Size of atom. The smaller the size of atom, greater its tendency to attract the sheer pair of electrons towards itself, and higher will be En value, which means atomic size increases, En decreases. It is pretty similar to Ea. And going from here, atomic size decreases, Ea increases, En increases. So again, if atomic size increases, En decreases and vice versa. So which means if atomic size decreases, En increases. Now let's talk about charge of ion. A cation is smaller in size as compared to its parent atom. We already learned about this. As a result, a cation attracts electrons more readily than its parent atom. Thus, a cation has higher electron negativity than its parent atom. So, basically, what it is trying to say is cation has more En than its parent atom because it is smaller in size. So we already learned atomic size, if it's small, En increases. That's what happening here. And similarly, for anion, since it is larger, the En will be less than its parent atom. So for example, because Fe3 is smaller than Fe2 plus and Fe, which means this will have the highest electronegativity. And since this is smaller, and this is bigger, this will have the higher electronegativity. So according to Mulliken scale, there is a formula to calculate electronegativity, which is electronegativity equals to ionization energy plus electron affinity by 2. Remember this. Electronegativity plus ionization energy plus electron affinity by 2. Variation of electronegativity in periodic table. In period, electronegativity generally increases from left to right. Generally increases. The increase is due to increasing effect of nuclear charge. Because the nuclear charge is greater as we go from here to here. So more force is attracted, which makes it smaller, which means atomic size decreases, so En increases. In group, generally, when you go down, En generally decreases when you go down because atomic size increases. We have already learned about this, but we are again learning this because this is another topic. It's not the factors affecting electronegativity, it's the variation of electronegativity in periodic table. This trend is primarily due to increasing atomic size and greater shielding effect. So going down, atomic size increases, so En decreases. So basically, let's take it like this. Here, En decreases. Here, En increases. This is group and this is period. Now let's talk about electronegative character in electronegative character in metallic character. Electronegative character increases across period from left to right and decreases down top to bottom. So basically, electronegative character increases going from here to here and decreases going from down to here because nucleus. Now metallic character, so basically metallic character decreases across a period and increases down a group. I will tell you again. Electronegative character and metallic character. So going across a period and going down. Electronegative character increases while going across a period and decreases as going down. But it is opposite. Here, it decreases at going across a period and increases as going down a group. Why? Because metallic character means if how quickly it can lose an electron. So when we go down, the cells increase, so the atomic size increase. So it is easier for the atom to give up an electron. So metallic character increases. But when going from here to here, the size decreases, so it is difficult to give. So metallic character decreases. So this was it for today. I will make another video quickly. So good night.